Swapnil, good morning. Okay, 8 have logged in. Okay. Ajay, good morning as well. And Anjali and Ayush, Shah, Saraswati, Shambhavi Deshmukh, all of you all, a very good morning. Karthik, good morning as well. Well, yesterday we spoke, Avikshit, good morning, Sushil, good morning. Yesterday we spoke about the theories of crustal formation. Obviously, Rishikesh, good morning. Obviously, we have only one of the theories. That's one of the pioneering theories, I would say. And that's all that's required as far as FIB is concerned. But for further interest, I said that, say, the continental drift theory further led to other theories, the convectional current, sea floor spreading, and eventually culminated into what is called as the plate tectonic theory. And interestingly, the plate tectonic theory is something which is something on which, as I said yesterday also, that thousands, if not more than that, are working. Pratik, good morning. Thousands of scientists in different parts of the world are working on that. So we have to be known to that aspect as such. After that, we need to go into the other aspect, the last topic, the Daviesian cycle. But again, jumping to the Daviesian cycle would leave you in Shraddha, good morning. Would leave you in a bit of confusion, and that is why. Just like we spoke about the basics of geomorphology, I'm going to take you through the scratch as far as this aspect is concerned. Of course, I'm going to be Avi Borade, good morning. You're going to be a bit fast there. And then when we come to the reverse aspect, which Daviesian cycle is related to, we are going to go into the details of that as such. But for the link, Isha, good morning. For the link purpose of your understanding as far as exogenetic forces are concerned, we would be going into the details of that. Endogenetic, we have just done one, that's the earthquake, and in fact that too we have related it only to the say the seismic waves as such. Okay, but with regard to the syllabus, now let us go to sharing. Let me see if I have sorry, I have not shared it, so I'll just go into the details of presentation. And I'll go back here and yeah, this is the slideshow. Yeah, let me share this with all of you all. What you would be seeing in front of you is basically everything that happens within geomorphology. Okay, you'll see that what is in front of you, it's only minus what happens within the earth. Otherwise, and that too as far as center is concerned, otherwise we have taken up most of the things in one slide as such. Interestingly, I had prepared this particular presentation for students who are studying for their talent search exams, and I thought that it would be useful for us as well, and that's why I am presenting it to you. I'm using this to link up everything. So we start with earthquake movements, and we have two types of movements, endogenic and exogenic. Today we are going to go into this part, but just to revise with what endogenic are, okay, you'll see that diastrophism and sudden movements. As far as sudden movements are concerned, you have, sorry, the spelling, I need to correct it. Earthquake is one, and volcano, both of them are sudden movements as such. Now, as far as diastrophism is concerned, You have epirogenic, that is on a very large scale, and orogenic on a minor scale. Now, though I say minor scale, and please understand that as far as the geomorphic scale is concerned, a mountain is a minor feature, and of course a continent is a much larger feature. And as a consequence, you'll see that when I speak about epirogenic movement, it's continent based, and two general movements, that's upward and downward movement. And when we come to mountain building or orogenic movement, these are tension and compression. Okay, now moving to exogenic forces. Okay, they are a combination of weathering, mass wasting, and erosion. Weathering involves, I'm sure you have done this in your earlier classes, physical, chemical, biological, and anthropogenic weathering as such. And as far as mass wasting is concerned, mass wasting is basically material coming down in the form of, or moving material under the influence of gravity only. So where the material sits where it is, that's called as a slump, and you have a topple where it just say toppling. You may understand the meaning of topple. You see that it just falls off. Okay, but at a faster speed, you call it as a fall, and a further speed you call it as a flow, and then a slide, and then you go slowly to creep and lateral movement as such. These are various types of mass wasting moments. There is another classification in mass wasting which is based on the type of material. Okay, if it is clay, then you call it differently. If it is sand, you call it differently. If it is mud, you call it differently. If it is rocks, you call it differently as such. What we are more interested in with regards to your topic, that's erosion. I'll just go back to this aspect as such. Yeah, here. Now, I would like to be a bit clear here that when we say erosion, some scientists say that it's one of the processes of erosion, transportation, and deposition, but some scientists refer to erosion as a comprehensive process. It's going to include everything as such. You may hear a bit of disturbance. If it gets very large, please let me know about it. River, glacier, coastal, karst, and wind are the major agents of erosion. What we have to remember here is that you'll see that in 4 of the top ones, except for the wind, water plays an important role. And as a consequence, we need to refer to a few of more things with regards to water as such. And what is that? It's here. Okay, you'll see that all the 4. Okay, I have see this one here is where water is in a solid format. Here, water is in a liquid format. Okay, and you'll see that right from the upper course where the rain is falling, it's coming all the way down here, and this is the mouth. Okay, of course, this is a very short replica of what the river does in its way, and it is to this particular cycle that Davis said that a river operates like a living being. Okay, it just like a living being has a youthful process, it has an adult process, and it has an old process as such. You'll see that just like life, he says that the river also follows these sequences, and that is what we are supposed to be understanding. Okay, you'll see that this is, of course, groundwater here, and then this is what happens along the beaches as such. Okay, wave erosion, you could say. This is the type of movement that takes place as far as transportations are concerned as such. Yeah, coming to what makes all this happen. Okay, the global hydrological cycle. I have 2-3 modules of these, and we would be discussing them one by one. You'll see that to start from this dotted line is supposed to be the, so to say, the boundary of this system called as the hydrological cycle. Solar energy is used for the evaporation. It's going to move vertically upwards. Okay, and then it gets condensed into water vapor, and this water vapor is going to move down in the form of precipitation. When the temperatures are very low, it gets stored in the form of ice. And then if it's, of course, if it melts down, it is going to run off and, of course, at times infiltrate through it as also. And it will collect here as groundwater. And through various median processes, there's going to be evapotranspiration from the soil, okay, from the vegetation, and so on and so forth. Okay, we'll go into another view of the same hydrological cycle as such. You'll see that the colors here are going to indicate, say the input, the storage, the flow, and the output as such. Okay, so precipitation is the input. Interception by vegetation is where it is going to be stored. Surface storage also. Then, of course, it starts moving, infiltration. It's going to move down into the subsurface rocks, and then it's going to level up here as the water table. Okay, these are a few terms. Through flow, water that flows through the surface is called as through flow, and if it is further down, then you call it as groundwater flow. Okay, these are a few terms that we need to understand as such. When it is going to flow over the surface, we call it as surface flow or overland flow. Okay, and of course, this is going to be the river channel, which is going to carry the water into the nearby areas as such. Okay, another view of the same, that's the hydrological cycle. Okay, this is say what we call in computer language as a flow diagram. But first, let us visit this diagram. You'll see that evaporation is taking place here, and then you have condensation. This condensation is going to lead to precipitation, melting. Okay, as it runs off the surface, you're going to have evaporation from here also. Okay, and what flows on the surface is also called as runoff. What flows into the surface is called as infiltration here. Okay, the infiltrated water starts moving horizontally. That's going to be called as groundwater. Okay, and this groundwater is going to recharge lakes. This is going to recharge rivers as it discharges the water into the nearby lakes and rivers. Okay, and further down, of course, groundwater is going to be stored. If you remember the other day in the movie Home, we saw what is called as fossil water. If water travels further deep down, very deep down, and it stays there, it's called as fossil water. Of course, it's very deep, and recharge of that particular water is very difficult, and that is why we saw in that presentation that how once the water is being used, the whole equipment it actually goes redundant, and you can't further use it anymore. Okay, so that's an environmental aspect about it, of course. So this is what again happens in a flow diagram: precipitation, interception, surface flow, soil infiltration, soil moisture storage, deep percolation, groundwater. I would further add here and say that you're going to have fossil water, but this is a cycle. You'll see this is a cycle, and that's why probably they have not added fossil water here. Okay, you're going to have evapotranspiration from vegetation, surface storage, soil infiltration, and soil moisture also, and this is going to add to the precipitation. Now, when it falls on the surface, you're going to have overland flow. When it moves on the surface and moves laterally, it's going to be called overland flow. When it seeps down and it moves parallel to the slope of the surface, it's called as through flow. And when it moves further down horizontally or laterally, you're going to call it as groundwater flow. All of this is going to build up channel storage, and this channel is basically a river which is going to give you the drainage basin output as this is another basic thing that we need to remember as such. Since we are going to speak about rivers, what all do we know about rivers? There are a few interesting things that you will find in front of you. I don't know whether I've discussed this earlier with you all. I have a feeling that I have done this, but even if we have done this, a revision of this is always interesting. You'll see that the longest rivers of the world. Let us discuss a few interesting things. When we speak about rivers, there are three terms that we normally refer to. Okay, these terms include what they. Just let me check if I can. Okay, you'll see that this point here, this is largest river. This here is the longest river. This here is the largest river system. Let us first, before we go into the details of these numbers, let us first understand what is the difference. What makes a river large, what makes a river long, and what makes the river a largest river system. Now, first let us speak about these two, largest river and longest river. We see that the longest river is the Nile and the largest river is the Amazon. Longest river is in Africa, largest river is in South America. The length, sorry, the Nile is 6,695 kilometers long. The Amazon is 6,400 meters long. Now, obviously, the longer of them is Nile, so probably the reason why we call it as the longest river. But one thing you have to keep in mind that when it comes to length, the Amazon is not less. In fact, you can see here that it's only 300 kilometers longer than the Nile. Okay, this is an important thing that you have to keep remembering. Then the drainage area. Now we'll go into the details of what basically a drainage area is. Okay, similar terms are say the drainage basin, the catchment area, and so on and so forth. Okay, it's all that area, that every drop falling within a particular area is going to be drained by this particular river. So that area comes to around 1 million square miles, 1 million square miles. And you'll see that Amazon is again literally double of that, 2 million square miles. Now, the kilometer age wise, you'll see that it's only a difference of 400 kilometers. But as far as square miles is concerned, the Amazon covers double the area, I would say, when we speak about drainage area as compared to the area covered by the Nile. Now, if you are not able to watch this, we'll go to a bit of enlargement of this. We'll be requiring these things. So now you can, I hope you can see it a bit more clearly, because I see that on the mobile screen you are not able to see that. So I've tried to enlarge it for you all. Yeah, probably you would be in a position to see it now, that the drainage area of the Nile is half of that. Now, what does that translate into? Okay, the last column, flow at the mouth. This is called as the discharge. How much of water is flowing at the mouth in cubic meters per second? Cubic meters per second. This is called as Qsex. This is called as Qmex. Cubic meters per second is Qmex. Now, where else is this particular terminology used? You must have seen that during the monsoons, when the dams are getting filled by the monsoon and the falling rain as such, once they translate over a particular level and the rainfall still continues, what is done as far as the whole process of water management in the dam areas is concerned is that they start releasing this water, and the next day you get this news in newspapers that so many cusecs of water was released from Koina Dam, so many cusecs of water was released from say the Khadakwasla Dam, okay, and so on and so forth. So they measure how this water is, how much water is actually being discharged, and in fact, that is something. So that means that when I'm calling the Amazon as the largest river, what am I meaning? I'm meaning that it is not long, but it is carrying a significant amount of water. And how significant? How significant? Let me bring an observation in front of you. If I total, okay, let us try it, okay. This is 1,500. So we'll just move this and we'll say that if this is 15 and this is 315, okay, and this is 175 and this is 126 and this is 196, this is 13, this is 420, 125, 195, 164, 75, 47, this is 15 again. If I'm going to put all of these together, okay, I may just exceed this number. I may, okay, just exceed this number just by a bit. So When I call the Amazon River as the largest river, the water that flows through the channels of the Amazon is so large that it is just a bit short of the next nine rivers. Say if these are the first 10 longest rivers of the world. Okay, the next nine rivers, you put all of them to a total. Okay, you'll see that they don't match up to Amazon. That gives us the amount of volume of water that may emerge out of the say the course of the Amazon. As compared to that, the Nile, you'll see that it's very meager, basically because we all know that for a significant period it passes through, say the desert of Sahara, and that's why you have very less, particularly when you compare it with the Amazon. But you'll see that the Yangtze River of China, okay, is significantly large. 35,000 cubic meters per second is its discharge. And the next largest river is the Congo. You'll see that lengthwise it's significantly small. But you'll see that when you compare its length with its volume with the longer rivers, the Yellow, the Yangtze, and of course the Ob River that's in Russia, the Mississippi also included. You'll see that the Congo, in fact, is the second largest river of the world. Let me also share this information with you. So, in fact, we could do the same thing with the rivers following. Okay, that the Congo is has a significant amount of discharge. Now, what is common between the Amazon and the Congo is that the fact that both of them have a equatorial location. Both of them are in fact flowing, I would say, east-west. Okay, not absolutely, but to quite an extent. On the other hand, you'll see that the Nile flows north-south. These are a few things that we have to keep in mind so that when we analyze geomorphology or in fact the rivers further, it becomes interesting to connect many things. Okay, so whatever you can remember out of this particular thing is interesting. Now, coming to the say the largest river system. Now, if I say that the Mississippi is the largest river system, you would say, sir, you are making an error there, because if you see the drainage area, okay, the drainage area of the Mississippi is somewhere around 1 million square miles, which is just a bit short of the Nile, but of course it's still a half of the Amazon, and of course it's more than the Ob River also. But the fact here remains that when we look for the largest river system, we look into all the major connections. Now, what do I mean here? I mean here that when I say largest river system, it is the Mississippi Missouri River. The Missouri is a tributary of the Mississippi. Now, if I add the area drained by the Missouri to the Mississippi, then it goes beyond Amazon, and then you call it as the largest river system. So, though I have labeled this as the larger river system, it's not the Mississippi only. We have to add the Missouri River to this. So, the Mississippi Missouri system is the largest river system, is what we have to say here. Okay, so these are important things that we have to remember. The longest river, the largest river. The longest river is not more than 400 kilometers long than the second one to follow. But as far as the largest river system is concerned, the area drained by the Amazon, if you're looking at individual rivers, is exceeding, and the amount of water, obviously if the area is more, the water is also going to flow. Add to that the equatorial forests, which contribute to a significant amount of rainfall here. Those of who are from the SSC boards will remember that in 10th standard in geography, you did comparative study between India and Brazil as such. And there you studied about the Amazon River to quite an extent as such. This is all that we have to know and remember from this particular longest rivers. Of course, let me also again tell you that this is not related to I have to change this. Where is it? Just a moment. Sorry. I have messed up with a few things. Pointer options. Let me come to arrow options automatic. Okay, so yeah. So after this, we need to go into the next agents of erosion, which are helped by the force of gravity. You'll see that if we had not had gravity on this planet, then we would have not seen these things in front of us. If you, I remember seeing a clip posted on Facebook on the say International Space Station, where they did these experiments with water, and what they did is they poured water into a tissue that they were carrying, and they soaked that tissue with water. And what the astronaut did is, once it was soaked full of water, he just squeezed the water out of it. And it was very interesting to see that as the water came out of that particular squeeze, it just tried to adhere itself to any surface which had some surface tension, and it got on spread on the hands of that particular astronaut, and it was very nearly moving around that particular surface that they were using to soak the water as such. So water on itself will move only when gravity plays an important role. It could be solid, it could be liquid, or any other form as such. Gravity plays an important role. So you'll see that a force that we actually tend to sideline when we are doing a lot of geography is gravity. And here is where the physics of science comes into play and picture, and the importance of the same, considering the fact that we have to understand the role gravity plays as far as agents of erosion is concerned as such. Okay, now let us go into a bit more as far as these aspects of um, river work is concerned. Okay, you'll see that this again is something that we have done, and the hydrological cycle, the evaporation, transpiration, condensation, precipitation, infiltration, and runoff as such. What is important is a few terminologies, say stream, headwaters, mouth of the river. I believe you are not able to read through this, but I'll help you with that. Uh, or what I'll do is next time, or when I post this on our group, I will enlarge the slides and then I will post it to your to our group as such. Okay, because this is not much required. This is something that we look into when we are doing PG. Uh, but a few things that I would like to share with you all is a term called as headwaters, waters which are in the upper part of the stream. Mouth is obviously where the stream meets a larger water body, not necessarily the sea always, but a larger water body as such. Okay, then gradient, of course, is the slope along which the gravity helps the water to move. Um, the channel shape, these are various types of channel shapes. Okay, further the velocity and the changes in velocity which occur when when the river tends to meander, as it is called. This is the channel shape once again. You'll see that this is a more deeper channel, and then you have a much broader channel. This is of course the young stage of the river. It's narrow and deep, and then you have in the middle course you're going to have semicircular and channels, and as the river enters its older stage, it becomes very broad and becomes very shallow as such. Okay, as far as stream gradient is concerned, uh, you'll see that in the upper course the stream tends to be very steep, and as you come, and that's one of the reasons why you'll see that the channels are steeper, because the gradient is steep. You will find that the energy which the river or the stream has is going to be more, and so it can dig deep. Okay, as a consequence, you're going to have V-shaped channels here. They open up into U-shape basically because the gradient has gone down. Okay, if you're not able to read, I'm just saying upper course, it could be somewhere around, at this scale, it could be 5 meters per kilometer. So the river is going to drop its height by 5 meters per kilometer. It could come down to 1.6, that's near around 1.5 meters per kilometer. So it's gone down, and it further goes down when you come down to the mouth, where it is 1 meter per kilometer as such. So it becomes very, and that is why you have a lot of deposition here, and you have a lot of erosion in the upper course. And in the middle course, you have partial erosion, partial deposition, but more of transportation as such. So this is something that we that would interest us to just make us know and understand a few things as that go as far as a river is concerned. A few more things I understand that this is not very clear, but I'll just it's not something that we need to understand more in detail as such. What are the factors which affect stream erosion and deposition as such? These factors include the shape of the channel, the roughness of the channel, if there are so to say some obstructions in the channel. Say this third diagram here, we have a bridge that has been built across, so that is an obstruction because a bridge requires foundation here down. Okay, then you'll see that there is another type of obstruction wherein you have a landslide which has occurred on the bank and a lot of material has gone down into the channel as such. Okay, and further here you have a narrow channel upstream, and you'll see that it may be narrow basically because the rocks here are very stubborn and they are very hard as such. But down here the rock has gone soft, so the moment the rock goes soft, you'll see that the channel has opened up. So many things are going to affect as far as the factors affecting stream erosion and deposition are concerned as such. uh, just a few slides ago, we were speaking about the slide on the rivers of the world. We were speaking about calculating the discharge. How are we supposed to be calculating the discharge as such? Okay, this is an explanation to that. Okay, we take the cross-sectional area. What is the cross-section? And then we multiply it by the velocity. How fast is the water flowing? Okay, so the cross-sectional area, you multiply it with the velocity that is going to give you the discharge. Okay, how do you measure the cross-sectional area? It's the channel width plus the channel depth. Okay, the width of the channel and of course the depth of the channel will give me the cross-sectional area. I'm going to multiply it in velocity and that's going to give me the discharge. Cross channel width is of course measured in meters, channel depth is in meters, velocity is meters per second. Okay, so the discharge eventually is going to be cubic meters per second. That is how we come to this word cumex, which is an abbreviation of cubic meters per second as such. This is how discharges are calculated as such. What are the factors which affect erosion and deposition? Okay, obviously you'll see that the grain size and the stream velocity are the two major factors which affect the erosion and deposition as such. Okay, you'll see that from clay to silt, from sand to gravel, okay, you would require higher amount of material to the velocity, higher amount of velocity as far as movement of these respective sizes are concerned as such. Okay, now as far as stream erosion is concerned, how does stream erosion take place? We are going to go into the detail of that, but three of them: hydraulic action. There are two more, but just to have an idea of it, streams get eroded by hydraulic action, solution, and aberration. What these are, I'll come into that. But then you have transportation. Transportation takes place in three forms. I'm not going to go into much of detail because, as I said, this is all PG, postgraduate material. This is not for you all. But dissolved load. Some material is going to dissolve into the water and is going to move along with the water. Some material is larger enough, but not large enough to sink down. So that's going to be suspended material. And of course, you're going to have very large material, which is bed load. Bed load moves in what is called as traction and saltation. These are a few terms that we need to understand. And deposition takes place in various ways. Okay, you have bars and other things. We'll go into the details of that at some other time. Okay, now you'll see that when water starts moving in a particular stream, how does it actually affect? Okay, as I said, that it has four major processes. Okay, we'll concentrate on this one rather than any other one. Okay, so you'll see that hydraulic action, aberration, attrition or corrosion, sorry, and corrosion. Okay, corrosion is also called as aberration, by the way. Now, what is hydraulic action? Hydraulic action, let me tell you that though we have divided this into A, B, C, D, all of them are making their impact together. They are going to make their impact together. Hydraulic action. Now, hydraulic action takes place in two ways. Okay, it's the sheer force with which water moves. Only water. Now, it's a very hypothetical situation that I'm saying only water, but from the point of view of science, I would say that the hydraulic action is the sheer force of sheer water only, not mixed with anything else. It's the sheer water. Now, what is the water going to be mixed with? You'll see that here, once the water starts gathering material, it's going to use that material to erode it further. Okay, so that is why for the theoretical purpose we separate only water, which will have its own force, and this force is going to use to corrode, or sorry, to erode, not corrode. So it's the sheer force. Many times you may have experienced it, that when you have to just wash your windscreens of your car, or you have to wash some place in your house, you just throw water. You just throw water, and the force with which you have thrown the water is going to carry a lot of waste with it. That is what I mean by hydraulic action. Of course, in the water sense of it, the force, the sheer force of water doesn't stop there. Another form of hydraulic action is that you can see the A here and the arrows here. Okay, what happens is this water, because it's a liquid, it's going to soak the material. Okay, the soil, it's going to soak. Now, it so happens that when the water starts soaking the water, when the soil starts soaking the water, or the rock starts soaking the water, it may swell. Okay, because it has now taken in a lot of water. Now, this is now the soil plus water, the weight added to that. Now, soil plus water, that's wet soil now, has much more weight than when it was dry. As a consequence, gravity starts operating on it if it's in a slope, and it may collapse into the water. And that is how you'll see that when you have flood times, you have the banks which collapse into the main course of the river. That's because of hydraulic action, that the banks become wet, and wet banks basically mean dry soil plus water, which is added weight, and because of that they are going to fall. So that is as far as hydraulic action is concerned. Then we come to aberration. Now, what is aberration? Okay, you'll see here B, and what are these three grains doing? Okay, they are scraping. They are literally scraping. So now, as I said, that the water has got its material, it has its own force because of gravity. Now it has the material also. Okay, it's like carrying a weapon. If a person has only hands, but then he finds some weapon, say for example, I have a stone, and now this is a weapon for me, I can throw this at someone. Water does the same thing. This is water, and it's going to carry this weapon in the form of the material that we have. Now, as it pushes the material is going to scrape. Okay, and it's going to score, SCOUR. It's going to score the base of that particular river, and it's going to scrape the sides. Okay, they should have shown it otherwise also. You see that it scrapes the sides, and of course it scores the base. Okay, this is called as aberration. This happens with water plus the material it is carrying. Remember, aberration is always water plus material. Hydraulic action is water minus material. What is the third thing? Attrition or corrosion. Okay, you'll see that the C here, okay, it's basically what it does is, while this material is being used by water, this material is going to bang into each other, because this is not a military parade wherein all the materials are going to move in a very systematic and a symmetrical way. No, it's not going to happen. So you'll see that the water is going this way and that way, and it's along with the water that all these material is going to go this way and that way, and in the course they are going to bang against each other. Okay, this material is going to bang against each other, and if it has enough force, this banging material is further split, go down in size as such. When a larger material, okay, they bang into each other and they go into smaller sizes, is going to be called as attrition or corrosion. Okay, so attrition is the decrease in the size of the material which is being taken by the water. And how does it happen? Its material clashes into material, and that is how attrition takes place. And the fourth one is corrosion. Corrosion is, okay, you will see that the A, B, and C are physical processes. Okay, they involve force. Okay, D is a chemical process. It involves reaction. Okay, you'll see that the water or the material which is going is being taken away is going to react with the material which is making up the bank, and this reaction, in fact, may cause say the erosion of say respective material. It may so happen, sorry, it may so happen that only one or two of the tens of minerals that are there as far as the bank of the river is concerned may be eroded. Okay, so that is as far as corrosion is concerned. Now, how does this happen? Okay, you'll see that these processes have started. Okay, these processes have started, and what will these processes now lead into? These processes will now lead into this thing happening. Now the animation has stopped, but this figure should be fine for us. Okay, you'll see that this flowing water, okay, if the gradient is more, it's going to have its own energy and it will dig deeper. Okay, so you're going to have vertical erosion. Okay, then of course it will see that the laterally also the river expands, so that is going to be lateral erosion. And headward erosion happens only in the upper courses of water, wherein you'll see that if I could show you this point here. Okay, what happens is water is going to accumulate. Now this is a very geometric block. We know that in nature we don't have this type of geometric block. It's for our understanding purpose that we have created this. Now you'll see that a lot of rainwater is going to flow on the surface, and it is going to fall into the channel also from various directions. Now what happens is, towards the upper side, the water will come and this will enter the channel from this point here. And when it's going to crash into the river channel from here, it is going to slowly open up that particular area. So you'll see that this V, okay, this V, okay, not vertical V, the lateral V, it keeps on extending towards the upper course of the river. That's the headward side. So vertical, lateral, and headward are the three basic processes of erosion which would take place as such. Okay, and you'll see that this is, of course, something related to oceanic waters, but just to explain the same processes as such, from a very small crack, you'll see that the crack has opened up and it's further opened up, and it's going to create a cave here. Okay, it's further opened up and it separates. Now, what is the difference between this and this? What is the difference between this one and this one? I purposely put it here. You'll see that what is happening in the sea in an inverted V. Okay, it's an inverted V. In the river, it happens in a normal V. Okay, so the processes of and that's what makes geomorphology so fascinating as such. You see that the processes are the same. It's only that you have to look at it from a point of view to understand what the process is. It's only that it's a V here and it's an inverted V there. Okay, so it's so very interesting to put together these materials into, and that's why uniformitarianism as a concept has got a lot of ground when geomorphologists are referring to that as such. Okay, so that is how the river erodes, and let us move ahead. As I said, we wanted when we spoke about the rivers, we spoke about the catchment area. Now, what is a catchment area? Let me tell you. Okay, I told you all I will be showing it to you later. This red line. Okay, the water which is going to, the rain rather, which is going to vertically fall within this red line, okay, all of that water is going to flow through these tributaries, isn't it? Okay, and it's going to gather in the river, and of course the river is going to go to the base level. That's the water body nearby. This red line is called as the drainage divide or the water divide. Okay, there are various terms. Different scientists will call it by different names. But what is it doing? Okay, every drop that is going to fall outside this will drain into some other river. But this part that you see in front of it, every drop that is going to fall this has only one way to go to the sea, through this process. Okay, so this is the catchment area, and the whole area, this is called as the catchment area. This line is called as the water divide, or this is also called as the drainage divide. As a few terms that we need to understand. Okay, now when I look at the river from the front, okay, the river could look like this. Okay, the channel could look either like this or it could look like this as such. Okay, but when I look at it from the side, it could look like this. This is called as the longitudinal profile. Okay, when we speak about drainage divide, this is something that could help us to understand what a drainage divide is. Rainfall falling here will go this way, and rainfall falling here will go this particular way. So these are the two types of drainage. This is the line, the drainage divide, and normally it is near to triangular in shape. Okay, you'll see it's obviously it will not be an absolute triangle, but it resembles a triangular shape, because at the base it's going to be broad and at the mouth it's going to be narrow. So eventually it could be triangular in shape as okay. This is also called as the watershed, water divide, catchment area. Now, as I said, that it's very interesting to understand a few more terminologies before we go into what we are actually supposed to be doing. That's the deviation cycle as such. Okay. Um, if I'm looking at a river, say this pen which I'm holding is basically a river. Okay, and water is it's a channel, let us say, and water is going to flow from this. If I'm going to look at this channel this way from the front, like now you would be looking, this is, you are looking at this channel this way, or let me take a paper and show, or we'll use this very way. Okay, so this is how you would be looking at the channel. Okay, you are either standing in the channel or you are looking at the channel, say in simple terms, a front view. This is called as the cross section of the river, the cross section of the river, because you are having a cross view of that particular river. But if I'm going to look at the river like this from sideways, okay, this is where the river rises, and this is where the river has its mouth. Okay, this is when I'm looking at it sideways, I'm going to call it as a longitudinal profile. This is called as the cross profile of a river. This would look U shape, V shape, whatever it is. This is called as the longitudinal profile. This is called as the longitudinal. The highest point the river rises, and the lowest point is the delta point, where the river is going to meet some other nearby water body as such. Okay, so this is one thing, and this diagram here, okay, this is a plan view of a river. When you're looking at the whole basin from the top, this is the plan view. So there are normally three views. Any diagram related to river is going to be in three ways. Okay, you're looking at a diagram which is a cross section, you are looking at a diagram which is a long section, and you are looking at a river diagram in a plan view. This here, this left side, this is a plan view. This again is a plan view. Okay, at the base, in fact, you'll see that what they have done, you can match these two together. Okay, this is the highest point. Somewhere here is going to be the highest point. This mouth is the lowest point, and of course, this is the water body. So, drawing a graph from this point to this point, this is the longitudinal profile. This is what we need to understand. Okay, then we come to the main purpose. Having understood what all has happened, let's come to the ideal stream cycle. This was given by W.M. Davis. As I said, that Davis was a very influenced by Darwin, okay, and his evolution. And of course, the whole world was impressed by Darwin. Davis was no exception. And born somewhere around 1847, 50, after 1840. And you'll see that Darwin, I can remind you that I spoke about this combination of Darwin Davis during that presentation when I spoke about general introduction to geography also. Davis says that when you look at a particular river, okay, if you carefully observe, okay, a river follows a cycle. What is this cycle? This ideal cycle. Okay, he uses an important term, ideal. Okay, before he says the stream cycle. The ideal stream cycle, he says, is not a literal time sequence. It is not like what we spoke yesterday, that when I divide the Pangea, it divides into two. No, the division may be dependent on various factors. So it will have a youthful stage, it will have a maturity stage, it will have an old age, after which possibly it may go into what is called as a rejuvenation. Okay, so if a river is to live for 1,000 years, it is not that the four stages could be divided into 250 years each. Okay, it's not that simple mathematics as far as a river operational is concerned. Okay, Davis comes up with his particular theory in 1880, and he says that, as I said, the river is going to follow a sequence. The first of them in the sequence is a youthful stage. Now, what are the characteristic features of the youthful stage? It will have a V-shaped valley. Now, why should it have a V-shaped valley? Because the erosion is going to be more at the base of that particular V. Now, why are you going to have more of erosion at this base? Is basically because the gradient is going to be steep So water is going to have more power, so it is going to operate like a saw. You must have seen a saw, and the saw keeps on cutting at the base, and that is why the shapes are V shape. You can see the V shape here. Okay, this erosion has started at this level, this top level, and within some period of time, now it's going to be dependent on what type of rock this is. If this is hard rock, it's going to take time. If this is soft rock, the V shape would develop very, very fast. As in the process of eroding this surface in the youthful stage to form a V-shaped valley, what are the various features that would develop along this particular course? You will have rapids. Smaller waterfalls are called as rapids. Smaller waterfalls are called as rapids. When the rapids increase in size, you are going to call it as a waterfall. That water is going to bounce off smaller elevations, rapid. When the water bounces off higher elevation, then you're going to call it as waterfall as such. Does a youthful stage have a floodplain? No, the youthful stage will not have a floodplain. Okay, the drainage divides. Okay, broad and flat, undissected by erosion. Okay, you see the drainage divides. You'll see this is the drainage divide. Okay, what is separating these two? Okay, this is called as the drainage divide. How is it? It's broad. The top one is very, very broad. You see, this I can give you an example of Maharashtra itself. If you go to Pachgani, if you go to Mahabaleshwar, the tops are very, very flat, and of course you'll see that they are not dissected by erosion. Okay, the valley in this particular stage is being deepened. Okay, the valley is going to go down, down, down. Okay. There are a lot of examples that I could say. All these rivers of the Sahyadris particularly, or the Himalayan rivers, are, so to say, in Himalayas, are in their youthful stage. Yes. Okay. So I would say the Ganga, for example, till it comes to Rishikesh, the Ganga, till it comes to the Rishikesh, is in its youthful stage. Okay. So that's something that you have to remember. Now, from the youthful stage, it will move to an early mature stage. What is the differences that you can find between this diagram and this diagram? You'll see that the V has opened up. Yes, it has deepened, but the V is not very sharp now. It is very a broader V now. Okay, you see then these tops here, which were flat here, they have been eroded, and now you have a very steep crest line here. This is a crest line, this is a crest line, this is a crest line. So this is when the river has started going or moving towards its maturity. Okay, the V has opened. Okay, the valley is still V-shaped, but as we can definitely identify a difference between this V and this V, this is going to lead to formation of floodplains. Now, what is going to happen is, because this is now going to open up, there is going to be area for the water to adjust its dynamics. So when it is in force, it will take up a lot of material, but when the water supply is going to drop down, it is going to leave behind deposits. These deposits are now going to cause and create what are going to be called as floodplains. These floodplains are going to have sand and gravel, okay, with them. As I said, the divides are going to be very, very sharp. The crest lines appear very sharply as such. The relief features are maximum. Okay, yes, it has gone down, but you can see the topmost point and you can see the bottommost point. So it has got deeper, and of course this is yet to erode. Okay, so the highest point and the lowest point are at maximum difference, and that is why relief reaches maximum. The reason why we call it as relief reaching maximum is that the tallest point and the lowest point, okay, the difference is the maximum in this particular stage. Okay, valley deepening has now stopped. Why has it moved from a sharp V to open? You'll see that valley deepening, I won't say it is stopped, but it is going to be very, very low as compared to what it was here. It was very fast here, and it has gone very slow here. Okay, so this is as far as the stage of maturity is concerned. Yes, we have to go into the late maturity, old age, and rejuvenation, and a few more to follow. But I think I should stop sharing here. And having stopped sharing, what I'll do is we'll go back to StreamYard, and let me have questions if you have any, as far as the Daviesian cycle or anything that we have done till now. If you have any questions, you can just ask me those questions, and if possible, I would be answering those questions. And if you don't have any significant questions, we would call it a day, and we'll continue tomorrow. A question I had for you all is, are we ready to shift to G suits now? Can we take an experimental session tomorrow on G suits? Examples of mature states. Yes, I'll come to that. In fact, we need to speak about examples in each stage. Okay. Examples in mature stage is going to be that the river starts meandering. You're going to have floodplains. Okay, you will not have many waterfalls as such. You may have rapids, but waterfalls definitely are not going to be there as far as the middle stage is concerned, or the mature stage is concerned. You'll see that the banks, they start getting steeper. Okay, they start getting horizontal. You'll see that they are V-shaped, but the banks start getting straight and steeper as far as the middle stage is concerned. I'll get you more examples when we meet for our next lecture. We'll discuss this again as far as our WhatsApp group is concerned, as to whether we should be shifting to our Google Classroom tomorrow, and we'll take a call accordingly. Let's stop here for the day. If you have any further questions, you can post them on the WhatsApp group. We'll stop here today. Thank you for being there, and I'm going to end my broadcast right now.